Hey everyone, this is Dr. Walker. This is video 234 and it is called Energy Transfer in a Circuit. Let's start off with a question. Why does this happen? A 75 watt incandescent bulb is brighter than a 60 watt bulb. So I know these days we're going away from the incandescent bulbs, but this is valid for incandescent bulbs. It's actually not really valid for your other bulbs such as the fluorescent ones or the LED ones. So just humor me with the incandescent bulbs here and tell me what you think in the comments. Why is a 75 watt bulb brighter than the 60 watt bulb? So let's take a look at how energy is transferred in a circuit. Let's imagine a positive charge moving through this circuit. This circuit has a battery here on the left and it has a resistor here on the right. This symbol here indicates ground, and when you ground something, then it's considered to be at a potential of 0 volts. So we have a positive charge that is going to move through the circuit. What's going to happen as it moves from A to B? So think about it. This goes back to our discussion on batteries in the previous video, where we learned that the charges gain energy because of the chemical reactions occurring within the battery. So from A to B, the energy is going to increase. What about from B to C? So from B to C is just a wire, and we've said that in any of our circuits, wires are not going to have any resistance, which means there's not going to be any energy loss for the charges as they move through the wire. And another way to think about it is that this wire is an equipotential surface. All the points on a wire that is just a plain wire all have the same potential. So let's say this is a 9 volts battery, then you have 0 volts and 9 volts. Then that means that point C would also be at 9 volts. So there is no energy change because there's no voltage change. So it doesn't change. I'll just put a horizontal line, no change. What about from C to D? So from C to D, we know that the charges are colliding with the resistor atoms and charges. So they're losing energy. The resistor is heating up as the charges flow through. That energy is lost to the surroundings. So we definitely have a loss in energy. And this loss in energy actually corresponds to a potential difference across the resistor. Remember in the previous video we talked about use Ohm's law, rewrite it as delta V equals IR to find the potential difference across a resistor whenever there's a current going through it. Now in this case we don't have any values for current or resistance, but if we have 9 volts for the battery, and we know that in the bottom here we have an equipotential surface, everything is at 0 volts, and at the top you must be at 9 volts. That means that the potential difference is negative 9 volts. There's a voltage drop across the resistor. There's a voltage gain across the battery. And just to remember, delta V is change in potential energy per charge. So if you lose energy, that means that the potential difference is negative, which it would be in this case. And finally, from D to A, we are at an equipotential. We have no voltage change, no energy change. So I like to just kind of go through this process just so we can have a better visualization of how the charges are gaining and losing energy as they are going through the circuits. And it's going to help us understand power a little bit more. So we talked about that the charge is moving through the resistor. That resistor is going to heat up. That energy is being transferred to thermal energy of the resistor. Power is energy per time. We learned that in Physics 1. So in this case, it's the rate at which the energy is transferred. We can say power is energy per time. So if we look at the definition of, delta V equals PE over Q, I have to write it out, and let's solve for energy here. So energy is Q times delta V, which I should have known that without writing it, but that's okay. If we rewrite the the energy, the potential energy that is transferred, then we write as Q delta V. What we can also do is we can rewrite charge per time. Do you know what that is, right? Charge per time, that's current. So we can see that the power, the rate at which the energy is transferred, is equal to the current times the voltage. And that's what this definition says. And then the other two definitions, they simply use Ohm's law to write the other two versions. For instance, if you plug in IR for delta V, then you get I squared R. And then you can do another substitution to get V squared over R. So when you have 2 out of the 3 variables, the 3 variables being delta V, I, and R, then you're just going to pick the equation for power that has those 2 variables that you have so that you can solve for power. And the unit for power is watt. This picture over here shows an infrared image, and it's showing our pieces of metal here heating up to different temperatures when they're heated, when they're connected. So it's showing that, hey, that there is power being transferred because you can physically see it glowing, and you can see the energy being transferred. Kind of see it, right? With the picture of how hot it is. Let's do a couple of questions. So the first one here says, how much current is drawn by a 75 watt light bulb connected to a 100 volt outlet? So watt is power. We have power. Voltage is potential difference. We have power and voltage. We're looking for current. So current is I. So go ahead and try it by yourself for a second. Pause the video and let's take a look. So the equation that we want to use is power equals I delta V, because it has all 3 variables. We're going to solve for current. That equals P over delta V. So we're going to plug in 75 over 120. And that's going to give us the current. And that's going to give us 0.63 amps. So this was a plug and chug using the definition of power. Let's do the final question here. A little bit harder. Which has a larger resistance, a 60 watt bulb or 100 watt light bulb? And I give a hint. Assume they're connected to a 120 volt source. The reason I give this hint is so that you understand that the voltage is going to be constant. When you plug in that light bulb, where your ceiling fan is, you get 120 volts, you get a constant voltage. So which one has a larger resistance? Well, we need an equation that has power, we need an equation that has resistance, and we also want an equation that has voltage, because we know that voltage is staying constant. So now we can see exactly how the power and resistance are related if voltage stays constant. So the equation that we want to use is the power equals V squared over R. This version of it has the variables that we want. The voltage is staying constant, so we don't have to worry about it. We can just look at resistance and power. So the one that has a larger resistance, because resistance is in the denominator, is going to have a smaller power. So which bulb has a larger resistance? The 60 watt bulb, because it has less power than the 100 watt bulb. So be careful with these types of questions. If you had used another equation such as I squared R, and you were thinking, oh, more resistance means more power, but the current is also changing. So we can't just say more resistance equals more power, because we don't know how the current is changing and affecting the power at the same time. So don't use this equation. Always use an equation for which you know that one of the variables is staying constant, so that you don't have to worry about it. That's all for this video. I will see you in the next video.